Hello, everyone, and welcome to today's fantastic webinar, Solving the Mysteries of the Quantum World. My name is Don McSweeney, and I am thrilled today to be joined by Professor Barry Sanders. He is the director of the Institute for Quantum Science and Technology and an international thought leader in quantum science. Barry and I had the opportunity to chat earlier about this topic, and let me just say that my mind has been sufficiently blown. Today we're going to be talking about a universe of infinite possibilities, a world where nothing is ever just black and white, and a world in which, of course, a cat can famously be alive and dead simultaneously. A world in which computers could solve problems in a matter of minutes that would take today's computers until the end of time, or at least until our sun implodes. In short, we are leaving the world of ones and zeros and entering the quantum realm. Now, as always, this is an honest-to-goodness two-way conversation, so really, please feel free to submit your questions throughout this webinar. Also, check out the great resources. You'll see them just to the right of your screen. And let's also make this a global conversation. Please take the conversation to Twitter using our hashtag, which is Explore UCalgary, hashtag Explore UCalgary. So let's meet our host, first of all, Dr. Barry Sanders. He has his PhD in quantum optics from Imperial College in London. He is an honorary Doctor of Science from Imperial College. He is a fellow of the Royal Society of Canada. He's been a professor here at the University of Calgary since 2003. And I've forgotten the acronym, Barry, USTC.
University of Science and Technology of China.
In China. And it says here you're a talents prof.
Yeah, China has a special program that recruits Chinese talent back and foreigners into the country. So it's a generously funded program that allows those people taking it up to do some great things in a country which is investing heavily into quantum science.
Well, very interesting. Barry, welcome, and I guess, are we really going to solve the mysteries of the quantum world in the next hour here?
Well, so the title is Solving.
Yeah,
so we'll talk about how we're going about solving, but fortunately, it's going to take a long time to solve all of them, which keeps us quantum physicists in work.
Well, I'm very much looking forward. So is a really large webinar crowd that we have joining us. People are obviously very excited to be part of this conversation today. Where should we start?
Let's start at the beginning. So the slide that you can see in front of you is titled Blackbody Radiation. In the year 1900, Max Planck figured out something very important about how hot objects glow. And so we traditionally date quantum theory back to 1900 and Max Planck's idea. And this slide kind of gives you the idea. You can see on the slide there's a spectrum, like a rainbow with red on the right, violet on the left, and you can see different curves that show temperatures. The sun, the surface of our sun is 6,000 Kelvin. So the curve that shows 6,000 Kelvin tells us how bright different colors of the spectrum are. Going left of the violet, it's black because we get to ultraviolet, X-rays, and we don't see those. From red to the right, it's all black. That's infrared, data, radio waves, and beyond. So we don't see it, but there's colors at every point on the line. And the question of how bright each color is vexed scientists in the 19th century. So there were theories that didn't employ any quantum principles. And the idea is that as you go further left on the curve, the brightness should get higher and higher and higher. But that can't happen. For example, if you do ceramics and you take pottery and put it in the kiln and you take it out, it glows. It glows reddish because of the temperature. But according to the theory, there should be more and more energy as you get more and more violet, and so much so it would destroy the universe. So in a way, you conduct the experiment, you do ceramics, put the pottery in the kiln, take it out, the universe doesn't get destroyed, and so you falsified that whole theory. So everybody knew there was something wrong with the theory.
You mentioned this one last time. So why, according to that theory, why would it destroy the universe?
Because you'd start getting infinite energy, let's say in the X-rays. There'd be so much X-ray in the universe that it would vaporize it.
So when the color goes, it means that the energy is now moving to these other spectrums.
Yeah, you can even, if you look at the line at 6,000 K, that's 6,000 degrees above absolute zero, That's the temperature of the surface of the sun. Once you go left of the violet, the curve goes down.
Right.
So the correct quantum theory of Max Planck tells us that it's not going to happen, that there's something that causes the curve to fall on the left.
Right.
And something turns out to be quantum theory behind it.
Interesting. Okay.
So that's the idea. And Planck, when he introduced it, he realized that there was a scaling to it, how fast it fell off. He put a constant. This is known as Planck's constant. So anybody reading about quantum will see Planck's constant. It comes out in this theory. It was interesting because Planck, when he did this, he, like many of the early quantum physicists, were allergic to the theory. So he says, this is the theory that explains it, but don't draw any conclusions that this theory is general. It's restricted to this case, and forget about it if you're doing any other kind of physics.
Right.
It took Einstein in 1905 with explaining the photoelectric effect, where he generalized it, and so it opened the door to say maybe this weird theory isn't restricted to one case.
Right.
But I wanted to show you that the hints of the theory go even further back to 1877 as an example. Ludwig Boltzmann. Boltzmann was a great physicist of the 19th century who wanted to understand how gases behaved, how thermodynamics in engines work, these kinds of things. And so he puzzled about the way atoms behaved. And in this picture, you can see his own drawing on the left, and below you'll see the short goo.go reference. So anybody who wants to look up the sources of these can just type that into the goo.go page and get it. And there he's trying to understand the spectrum of iodine gas. So we know iodine. Iodine is added to salt to help our thyroids function in landlocked areas. And he tried to explain the spectrum that occurs when iodine gas goes. And so in the picture, without explaining in detail, the picture is kind of showing Boltzmann's thinking, where he realized that the energy change occurred in a discrete way. So when you drive a car up a hill, you put your foot on the gas pedal and you go up higher and higher, your energy is increasing. We think of it as increasing as a continuum, that it's going in a way that, when it starts at one energy, finishes at another energy, every energy along the way has been touched. What Boltzmann was starting to realize is in the iodine molecule, the energy did not change that way. It jumped. This is something we now call a quantum leap today, or a quantum jump. We use both terms. And so Boltzmann started to recognize that the iodine spectrum was a result of discrete changes of energy.
Right. So in other words, energy, like to use your car analogy, it's not gradually moving through sort of a progression. It's going from one and then down. It's going to another.
Yeah, it leaps suddenly. It's jumping from one energy to another.
Right.
For the car, the jumps are so small we can't discern them. But when we get down to atomic and molecular scale, we can start observing those effects.
And that must have huge ramifications.
Exactly. This is what my whole career is about, exploiting these ramifications. So I thought I'd show you then, just to give you an idea of the ramifications, as you asked. One of the great discoveries was of helium. So helium is special amongst the elements that it wasn't first discovered on Earth. It was discovered by looking at the sun. And you can see, so on the left, that shows what a simple picture of what helium is. It's got a nucleus, 2 protons labeled P, 2 neutrons labeled N, and then 2 electrons going around. And nobody had seen that element on Earth or known or identified it. But then what happens, you can see on the right, there's a spectrum. And so I showed you the picture of black body radiation, and you saw a very smooth curve that showed how the brightness changed continuously as we changed color. But the helium spectrum shows very sharp lines. It means certain colors occur and the rest don't. And in the lower left, this is showing how we can see it. So we might look at the sun, look at the rainbow and its strength, characteristic of the 6,000 Kelvin temperature at the surface, and then we might see some dark lines. And the dark lines occur because the helium in the sun absorbs some of the light and scatters it. And those dark lines turn out to identify helium. And in fact, and you can see the picture of the sun in the lower right, and the concept of the idea that helium was a unique element in the sun is one of the great discoveries. And in fact, the word helium comes from the Greek word helios, which was the name of the sun.
Oh.
So there are ramifications. Discovering helium, which is really important now, it's extremely important in physics for making things very cold. So the coldest temperature we get our instruments in the lab is based on liquefying helium. And where would we be without party balloons? Everybody needs those. Then I thought I'd mention that in modern days, we're sufficiently advanced that we can just say, well, we need an atom with these properties. So in the old days, say 100 years ago, we had the atoms in the periodic table, and we used those. And nowadays, we can say, well, we need a designer atom. So let's build it. And on the left, I thought I would show you a picture. This is the crystal structure of diamond. So those white balls are carbons, and diamond is simply just a three-dimensional structure of compressed carbon. Nothing special. It's expensive, but it's material's cheap. And then what we can do is to make what's called a defect. So we throw away a carbon, put in something, in this case, nitrogen. We could put silicon. And in fact, this occurs in nature when this happens. Diamonds glitter. And the most expensive diamonds in the world are expensive partly because of size and partly because they glitter with the right features, pink diamonds, blue diamonds. Those are artificial atoms. So we can now make diamond, create these artificial atoms, and play with them. On the right, in this complicated set of diagrams, we can make atoms out of superconducting circuits. So a wire conducts electricity, copper wire, and it has resistance. But if we use the right material at a very cold temperature, we can make resistance go away. So we can make a current that goes in a loop and will never stop and never change if it's not interfered with. And through that, we can then make use of the magnetic field produced by the current and make that into an artificial atom. And there's many other ways I didn't show here, but we're getting very good at building artificial atoms.
And this all started with this idea of discrete energy.
Yes.
And being able to look at where those jumps occur to identify things in the different spectrum.
Yep, and now we want to make use of these jumps.
Right. So I know it's just as we go here, we just want to make sure that we just keep in mind that people are asking a few questions in here, and some of them here I think we're going to get to, including the obvious question of what does the term quantum actually mean? But
I'm happy to deal with questions.
Do you want to get to that one now, or do you want to address that as we go? What do we mean when we talk about quantum?
Well, quantum, I think, is like the word quantity. So the word quantum refers to that discreteness, the idea that if we go from one energy to the next, not in a continuous way, but in a jump, we think of it that if the energy changes, it's as though a packet of energy left the system or entered the system. So we increased the energy by a jump. A quantum of energy came in. We have to balance the books. So if the energy changes in the system, there has to be a compensating energy change in the rest of the universe. That quantum refers to the packet of energy that allows us to do these discrete jumps.
It's a good time for that question. Then.
Yes.
Yeah, okay.
Yeah, I'm so used to the field, I use the words and forget that they're not in everyday use.
Well, I have a quantum jump in my understanding there.
So then, going on, but let me know if there's any questions on how.
Yeah, we'll, as they come up, we'll bring them into the conversation.
Okay. Then on this slide, this is the idea of photons. So I mentioned the black body radiation, and the idea is that something glows. When an object glows, it's made of matter, ceramic material, if we're talking about pottery, and it emits glowing red light, and so quantum theory tells us how matter emits light and how light interacts with matter. But we now think of matter as described by a quantum theory and the light as described by the quantum theory. On this slide, I want to explain the idea of light behaving in a quantum way. We use the term photon. The photon concept was first introduced by Einstein in 1905. He didn't use the term photon. That came out in the 1920s. And photos is light in Greek, and so a photon The on at the end is a particle. So a photon is a particle of light. This is the quantum. So if the energy changes by light coming in a packet, that packet is called a photon if the packet of energy is light.
Okay.
And in the upper left picture, I'm just showing standard picture of an atom, the blue nucleus at the center, an electron orbiting, and there's two different orbits. The electron's in the lower orbit, it's a lower energy. Orbit's in the higher orbit, it's a higher energy. And then if it falls from the higher to the lower orbit, that packet of energy, that quantum, that photon is emitted. So that picture is showing you that for an electron to lose energy, it has to jump discretely from one orbit to the next. It gives off that photon, and that discrete jump is what we're seeing in that spectrum, in those lines of helium. Photons are tough to understand. Einstein once said, every Tom, Dick, and Harry thinks he knows what a photon is, but he's wrong. Something like that. And so the way I think about it, when you do quantum physics, you know, for practical purposes, it's tough because there's philosophical conundrum. But I tend to think of it, a photon, as something that makes a photon detector go click. So first I say there's a detector, and when it clicks, it's a photon. And if I think that way, I avoid the philosophical difficulties. And in the lower left, that's just a picture from a catalog of a photodetector.
Yeah, I mean, but speaking of discrete packets of energy, I'll never look at Captain Kirk's photon torpedoes the same way. But
you can count them. So then on the right, I just thought I'd put in the picture. I'll explain in a moment. But this is the idea that we don't have to make one photon at a time. We can make two. This picture was picked by Physics World. It's the physics organization in Britain, and as one of the top 10 iconic pictures in physics of the 20th century. It comes from a group in Innsbruck. They did an experiment in the 90s. And the two bright green spots, so you can see they're circles. The circles refer to conical beams, like an ice cream cone coming out of the screen. Where the green intersect, those two green photons are entangled. And I'm going to explain entanglement. That's one of, so far we haven't even got to the hard part. So the hard part's coming up.
Yeah, we have a question from Anna asking if we can explain the quantum theory of time. Hold on, Anna, we're gonna get there. We've got a little bit to go, first of all.
Yeah, good idea. Yeah, quantum theory of time I'm happy to get to later. Okay, then I just thought I'd mention here that photons are one kind of energy exchange, but once we get inside the nucleus, there are other kinds, and it's a little bit more complicated, but in this picture in the upper left, you can see a decay. There's an electron, E- emitted, and what is going on here is a neutron will convert to a proton, and a neutron has no charge, proton has a positive charge, so an electron is also produced in order to balance the charge. You know, if you start with no charge, you have to end with the sum of charges being zero. And there's an antineutrino. So it's some sort of antimatter that I won't go into now. And those three particles balance the energy, angular momentum, charge equations. And the way that that works, in the lower right, you can see the neutron is made of quarks. It turns into a proton. But the important part is there's this W- that leaves. And the W- is like the photon for what we call the weak nuclear force. So if we can understand how photons work, and we know there are only four forces of nature. There's the light, and there are two nuclear forces, and then there's gravity. Gravity we don't understand yet. But the other two forces are kind of like photons, a little more complicated. So the question about the quantum that I explained is a packet of energy to balance the energy equation, and it's discrete. If we deal with nuclear forces, in this example, we have a W particle. We have a Z particle also. And then we can have gluons, which are another kind of nuclear force. So we actually know every type of quantums, if we forget that the universe has gravity, which we don't understand.
And when you're looking at these systems, right, there has to be something to make that electron, you know, get booted out of that atom. Are these the things that cause these discrete energy jumps, these are them interacting in the systems, or?
Well, yeah, in a way, the reason that the electron, which is a beta particle, if people know alpha, beta, gamma radiation. In my way of thinking, the reason is, like, the question is, why doesn't it go somewhere? And the answer is, the nucleus has a wall around it that holds it in. But the wall isn't good enough to keep it there forever. So you can think of the particle as bouncing around, and every time it hits the wall, it has some probability of getting out.
Right.
So the way nuclear decay works, at least for alpha and beta particles, you can think of something as bouncing around each time with some chance of leaving, like a coin flip, and then it exits.
Okay.
So the answer is that in quantum theory, if something is not perfectly confined, it can get away. We call this quantum tunneling.
Thank you.
Okay, you're welcome. Okay, so here, this picture is taken from the web. Douglas Hofstadter wrote this. Any Big Bang Theory fan might recognize the name Hofstadter. One of the lead characters is Leonard Hofstadter. And the name Hofstadter for Leonard Hofstadter is named after Douglas Hofstadter's father, who won a Nobel Prize in physics. But Douglas Hofstadter is no slouch. He has an amazing intellect in his own right. He wrote the book Gödel, Escher, and Bach for anybody who read it and appreciates recursiveness in nature. And he tried to capture the concept of quantum mechanics just on this slide. So when you read the slide, you can see clearly light is and then there's a somewhat obscure word below. Some of you might see the word particle, and some of you might see the word wave. That's the point. So it says both. And so Douglas Hofstadter is conveying the message that light, but it could also be matter. Each thing can behave as a particle or as a wave, depending on how you look at it. So a particle is a point-like object that in interactions conserves energy. It conserves momentum, how fast it's moving times its mass. There are certain things about it, but it's indivisible. And a wave has the property it superposes. Create two water waves in your bathtub, the waves cross through each other. They're delocalized. You don't see a wave as at a point. The wave is spread out. So the idea that everything in nature can be seen as both under the right circumstances is the essence of the weirdness of quantum mechanics.
It's kind of interesting, though, because, of course, the water in your bathtub is, hydrogen and oxygen atoms at any given point, but it's also a ripple of the wave.
Yeah, we just make the wave out of matter in that case. But then in this case, we would say even the H2O that makes water itself can behave like a wave. One water molecule can behave like a wave under the right circumstances.
Right.
So that's the idea. I mentioned entanglement before. So this is a weird idea that this is a duality of nature, but it gets weirder because if we start taking two particles, I showed you the two pictures showing two green photons, two particles behaves especially weird. This is where the real philosophical problem comes up. So I'm going to explain it to you in the context of Schrödinger's cat. Erwin Schrödinger, he once made a quote, something to the effect that if I'd known about these damn quantum jumps, I wouldn't have got into quantum mechanics in the first place. So he felt the quantum jumps, this whole idea of the quantum, was counterintuitive. And so even though he's one of the great founders of quantum mechanics, he objected to it. But he objected on good grounds. So he raised the following paradox. Now, as you said in the introduction, something being both alive and dead, but we kind of, as human beings, we hold sacrosanct the concept that life and death are meaningful. The Americans have the saying that only two sure things in life, death and taxes. And I'm about to show you that only taxes is the sure thing. Death is not certain. So the concept of the Schrödinger cat is, he conceives of a cat inside a box. The box is not transparent. You can't see what's inside. So you see the cat sitting on a platform in the box, and there's a canister that has poison gas, and if the poison gas is released, it will kill the cat. We don't actually do the experiment. We can't pass the ethics committees on this, but that's the concept. Then inside the box, think of one radioactive nucleus. And the radioactive nucleus, in this case, I told you about beta decay. This will be alpha decay. An alpha particle is really just a bare helium nucleus. So I showed you the picture of helium, 2 protons and 2 neutrons in the center, 2 electrons. Alpha particle is just like that with the 2 electrons removed. So an alpha decay can be thought of as an alpha particle trying to get out of the nucleus. And as I mentioned before, you were asking about how the electron gets out. The alpha particle is inside the nucleus because the nucleus has a wall around it. And the alpha particle is hitting the wall over and over, trying to get out, and then it can get lucky. And so on the right, you can see the alpha particle left the nucleus. If it leaves, it triggers the poison gas and the cat dies. If it hasn't got out, the cat is alive. But getting out in quantum mechanics is described as quantum tunneling. And in the structure of the theory, we never say it is in or out at some random time. The Geiger counter tells us it happened. But without the Geiger counter, we say at every moment, the nucleus is in a superposition of being inside and outside. Both realities coexist. So there's no sense in which we can describe the particle as being inside and outside. But that means that the cat is in no way described as being alive or dead. All you can say is logical statements. If the nucleus is inside, cat's alive. If the nucleus is outside, the cat's dead. And it's a superposition or coexistence of both realities.
I didn't ask you this when we talked about it earlier, but how did this articulation of this theoretical idea of quantum physics, how was that met by the rest of the physics community?
Well, these ideas were coming out in the 1930s. So what happened? Quantum theory emerged, the formulation of Planck was 1900. Einstein got some great ideas in 1905. There was what's called the old quantum theory, explaining spectra until the early 20s. And then the serious formulation came along. Schrödinger was one of those. And then they started to understand the consequences. So in the late 20s, they're doing their calculations, and they realized, and they debated, there were famous debates that went on in Copenhagen about this. And then they started to articulate the problems. Einstein pointed out a problem with entanglement, so did Schrödinger. And so in the early 30s, the serious, philosophically well-grounded scientists are saying, this theory is not compatible with any reasonable approach to the philosophy of science. Then it took more mystical types. Niels Bohr, who grew up in the Danish school, and he was much more comfortable with a more mystical way of thinking, argued back. There's the famous Bohr-Einstein debates, which are great reading, and so it really took a revolution in philosophy to move to the point where people were comfortable with quantum theory. But the comfort comes with the caveat. We still know there are inconsistencies. So we got to a point where we're comfortable with it, but we don't pretend we know all the answers.
Speaking of knowing all the answers, there are a few questions coming in, but it looks to me like we'll probably get to these towards the end of your presentation, but somebody wants to know the relationship between quantum physics and the way we experience reality, or is this something the new era stole from modern physics to explain things that we just don't understand? Somebody else wants to know, are there any other interactions beside the weak nuclear force that can cause the nuclei to change from neutrons to protons and vice versa?
Okay, so let me answer both now.
Okay.
The first one about the connection with reality, in the struggle to understand Schrödinger's cat paradox and other problems, there were discussions that took place, various what we call interpretations. So there are different interpretations, from the many world interpretation that's popular in science fiction to my favorite, which is known as shut up and calculate. We have a mathematical structure. I said a photon is what makes something go click. And so we just solve the problems. We have a consistent structure. But one of them, Wolfgang Pauli introduced, and this is carried on over time. Penrose at the University of Oxford and various others found this. And this is the question of consciousness. And so there's a lot of stuff written, some of it good, some of it bad. But the question of if there is a reality, so I'm not sure there's reality, but if there is a reality, then some people argue that reality is formed in the mind, and then quantum theory doesn't apply to the mind itself. And so it's consciousness, which we don't understand very well, which is the transformational moment. So that's one of the interpretations.
Interesting.
And the second question was about the weak nuclear force.
Yeah, interactions besides the weak nuclear force that can cause the nuclei to change from neutrons to protons and vice versa.
So we have, in nature, we believe there are 4 forces in nature. Now, that 4 could change if one day we see something new. But all of our observations can be explained by 4 forces. The 4 forces, one is light. Second is that weak nuclear force that turns neutrons to protons and gives off beta radiation. The third one is quarks. So the proton itself is made of 3 quarks, 3 particles stuck together that should fly apart. So the strong nuclear force glues them together, and then we call the packet of energy a gluon, suitably. And then the fourth one is gravity that I'm avoiding. In fact, the first 2, light and the weak nuclear force, are 2 sides of the same coin. So we call this the electroweak force. And there was a Nobel Prize given for the electroweak force. So they look like 2 different things, they look like 2 different things when we study them, but they're 2 parts of the same theory. And then the Higgs boson, which got a Nobel Prize a couple years ago, kind of showed us that actually there's one theory for light, the weak nuclear force, and the strong nuclear force, and we physicists like to believe there's only one force in nature. So the question is saying, is there another force that would explain neutron to proton conversion? We physicists are going the opposite direction. We would like to think that all of the forces are one. There's one force in the universe, and they look different, but when the universe started right after the Big Bang, we think that they were all one force, and then as the universe got colder, they manifest in different ways. So I'll just mention that we don't see any reason to put in another force, and it goes against the grain of how we think.
Interesting, and that sort of gets to another one of John's questions, where he asks how quantum field theory fits in.
Quantum field theory is harder because I talked about waves and forces, and then quantum field theory is a way of describing the forces, and it turns out that because matter is waves and waves are matter, we can actually treat matter in the same context as the forces, and it'd be a whole other webinar to get into.
Yeah, well, we have many other slides we want to get to, but I just want to quickly say that we did have a question here. It said, Professor, can you explain again how the two, I guess a question about superposition, how these 2 states can coexist? My mind still has its binary mode on, mutually exclusive.
Oh, so you need to quantize your brain. Then you have, your brain is then in a superposition of accepting and rejecting the statement.
Yeah.
Maybe that'll So read the question again.
It says, can you explain again how these 2 states can coexist?
Yeah, how they can coexist. So it's hard to, they just do, in the sense that we see things in nature, and then we try to come up with a consistent theoretical description. So when they coexist, in a strict sense, it's that the mathematics, the only mathematical structure we can explain our observations, says they do. But you're looking for intuition. You want to know what it is. How can I think about it? And the best way I find to think about the problem is to understand this coexistence in waves. So if you're in a room with different conversations going on, you're having a conversation, creating sound waves, and another couple are having a conversation with their sound waves, and the sound waves are crossing each other and oblivious to each other. And where the sound waves cross, so sound waves are just compression, rarefaction, low air density, and they travel, the compression waves travel along. And where they cross each other, you might get double compression. So you, in a sense, the coexistence is really about a way of adding waves together. So in that sense, the idea of the nucleus with the binary choice, is the alpha particle inside or outside the nucleus, the superposition is saying, well, think about it being inside the nucleus, but write a wave. And the wave would be written as some wave with most of it, some oscillating diagram. Most of it is inside the walls of the nucleus and a little bit is outside. And then the decayed nucleus is a wave where most of the wave oscillation is outside the nucleus and a little bit inside. And those two waves can coexist. You just have a sum of two waves. So in order to grasp it, you have to get to the point where you say, well, that binary choice about the nucleus is no longer a point particle. It is a wave. The wave has infinite extent. So is it inside or outside? Well, some of it's inside, some of it's outside. That's the coexistence. I can't do better than that.
I think it's pretty good. There's a couple other questions, Schrodinger questions here, but I think we're going to have time at the end. Let's move along and let's get back to some of these other questions.
Sure, and it's good. Yeah, so Schrodinger stuff. Well, here's the cat. So you see the picture, and then I'll go to the next slide. And the next slide just reminds you of the sequence that the alpha particle, that helium nucleus, hit the poison gas triggered the gas, kills the cat. And below, this is that coexistence. But we now are talking about two particles. So instead of saying a particle so matter can be wave or particle, or light can be wave or particle, now we're considering two. And this is the essence of Schrodinger's objection, the conundrum, the paradox, if you like. And so below, you can see the undecayed nucleus and a happy living cat. And it's inside of a special kind of brackets called a ket. And it's named, Dirac named it a ket. There's a vertical line on the left and an angular bracket on the right. And this just reminds us it's quantum. It means that we can think of them like waves. And we're going to add, the plus sign means it's summing waves. On the right, you can see another ket. And inside there's a decayed nucleus and a dead cat. And so that plus sign is telling us that we have a joint wave for the undecayed nucleus and our living cat, and a joint wave for the decayed nucleus and the dead cat, and they coexist. And so Schrodinger is saying, how can this be? That you have the cat is correlated somehow with the state of the nucleus, but the state of the cat is not definite. We can't say the cat is alive or dead. Then you can take the shut up and calculate view and say, so in practice, this is the open the box. Look at the cat. Then you say, well, I looked at it. This is the moment that the cat is alive or dead, when I look. And this ties in with the consciousness type article. So a conscious being looks at it and makes it alive or dead. But then you can imagine, and this variation is known as Wigner's friend. So in this case, Wigner's friend opens the box and looks at the cat. But Wigner's friend is in a larger box along with everything else. So quantum theory tells you that you just, instead of two things inside the cat, we have three. We have an undecayed nucleus, a living cat, and Wigner's friend seeing a living cat. Plus, decayed nucleus, dead cat, and Wigner's friend seeing a decayed cat. And then you have what is called a catastrophe, von Neumann catastrophe, that this can go on forever. So this is one of the big challenges to the consciousness view, unless there's a way that consciousness transcends quantum theory. So, this captures the essence of the problem.
Didn't take long to get into the whole mind-blowing thing, really.
Yes, literally.
Literally.
So here, I just thought I would show you this picture. So then you take a photon as a particle, and here, that M refers to a half-silvered mirror. So if anybody's been unfortunate enough to be interrogated by the police in an interrogation room, and I don't know it personally, but I know it from old crime shows. There's somebody there, and somehow the person inside doesn't see everybody looking outside, and usually seems to forget there's anybody looking in, and the people outside see everything. That's a half-silvered mirror. Same thing here. That M is the half-silvered mirror you see in crime shows. P1 and P2 refer to photon 1 and photon 2. So we're now going to have two photons, and the two photons come, and they hit a half-silvered mirror. If you think of the photon as a particle, each particle has a 50% probability of reflecting. So P1 has a 50% probability of reflecting to D2, that's photon detector 2, or transmitting to photon detector 1. Same with P2, 50% probability of each. So you expect to see half the time one photon at each detector, and half the time two photons at either detector. That's not what you see. So below, you can see blue lines and red lines. And the photons are also waves. So what happens, in the first picture, you see a blue line reflecting, that's P1 reflecting, and the red line transmitting. And then they both hit detector D2. The last picture on the lower right shows the P1 photon transmitting and the red photon reflecting. They're actually the same color. Blue and red are just done to illustrate the difference. And in between, we can see two possibilities. Both reflect or both transmit. In classical theory, we just add the probabilities. But in quantum theory, we have waves. And the middle two possibilities cancel out. It's a destructive wave interference. So we see both photons. We only see both photons go one way or the other. And that is not understandable by thinking of the photon as a particle.
Right.
So that's another weird thing. But this is actually one of the most important applications of quantum theory. We use this in my field of building quantum computers if we want to use photons. So these ideas, it seems less mind-blowing than Schrödinger's cat, but it is mind-blowing, and yet it is a tool of choice. And then it's weird, and I thought I would just put up a slide here. This is a simple diagram that shows a Bell inequality test. Now, let me tell you what happened. So in the old days, there was objections. Einstein, with co-authors Podolsky and Rosen, said quantum theory is surely not sensible. You know, it violates any reasonable philosophy, so there must be a greater theory that exists of which quantum theory is a special case. The problem is, how can we find a theory that replicates everything we see in quantum theory and doesn't allow information to travel faster than the speed of light? If you could send information faster than the speed of light, you could, that's very applicable. You could send messages backwards in time to yourself and beat the stock market. So if we ever figure that out, you'll see a lot of rich physicists. This picture shows how the experiments work. And there was an experiment done a couple of years ago, 3 experiments. One that was done in Netherlands using diamonds that I described, and then 2 more. And those 3 experiments proved that either quantum theory is completely correct with no extrapolation, or there's some weird conspiracy version, such as maybe at the beginning of the universe, all the initial conditions were just right to know you would do the experiment at that moment and make it appear wrong. You know, so we can't ever prove that quantum theory is totally correct, but we're cornering the conspiracy theories, that if there's some grand cosmic conspiracy to convince us that quantum theory is right when it's wrong, those conspirators are getting a tougher and tougher game to beat. So we think quantum theory is complete against what Einstein was trying to argue. Nothing wrong with Einstein's argument. It was early in the piece. And
the Bell test is sort of one of those smoking gun pieces of proof.
Yeah, it's kind of definitive. It follows a logical argument that's so tight that there's no reasonable alternative to explain. That S in the picture is that source. I showed you the overlapping rings with the 2 green photons. That's what that source is. It produces 1 photon going each way. A and B are 2 parties that are far apart so that the speed of light, they far enough apart that if they tried to communicate with each other to cheat, they would have to beat the speed of light to do it. They each change a local setting, and that CM is a counting module that counts when the detectors see a coincidence or not.
So if the theory of quantum mechanics is right, what would you expect to see?
We expect to see that the counts are greater than a classical description of the source would allow. So we say, let's suppose that classical theory is right. So we have probabilistic theories that don't allow communication faster than the speed of light. And we say, what is the probability of seeing this coincidence between, say, detectors D plus on the left and D plus on the right? Subject to changes in local settings, little a and little b. We see that those coincidences violate any theory. We don't even come up with a classical theory. It's for every possible classical theory, we show it cannot explain that rate. And you see a coincidence rate that exceeds anything that's possible by the principles of logic.
Wow.
That's the idea. So this becomes important. here I just put down a slide of public key cryptography. So one of the great applications of these ideas is we're trying to figure out how to make the world safer for encrypted communication. And we rely on this. On the left, you can see Bob. And Bob wants to send a message, hello, Alice, to Alice. And hello, Alice somehow is such an important message, he wants to make sure nobody knows what he's sending. Doesn't want anybody to know, anybody to know that he's talking to Alice. So he encrypts it. And then he sends to Alice that hexadecimal string, and she decrypts it with her private key and sees the message. There's a public key and a private key. So the way that our public key cryptography works, when you put your credit card number in the internet, if you're going to buy products from a company and you verify that company, the encryption, important part of the encryption is generating these keys. And generating them is very easy. On the right, you can see a T-shirt you can buy that tells you the standard algorithm we use, known as the RSA algorithm. So you wear your T-shirt, you can look in a mirror to remember the algorithm. If you can't read backwards, you can set up 2 mirrors to see the reflection of your reflection. And then you're able to solve, you're able to encrypt. And you can see the word prime. And the idea is that somehow finding prime numbers, so you write a number, and it's a product of 2 primes. A prime number is a number divisible only by 1 in itself, and it's hard to do. And the hardness of that problem, but the easiness of verifying, underpins our security. If you want type 1 crypto, the kind that in the United States they use for the most secret communication, then you'll use the Canadian invention of elliptic curve cryptography, shown in the lower right, and that's easy to solve, but hard to solve, but easy to verify. And that's how we do our crypto. The problem, as I'm going to show you, is that a quantum computer breaks this. So every version we know of today to do public key cryptography is easily broken by a quantum computer. So that's a practical application. It's kind of practical application like nobody really wants a nuclear bomb, but it's practical. So nobody really wants this, but it's certainly a practical application we have to study.
Yeah.
So that's the idea. And then this picture is trying to get across to you the idea of what quantum computing is about. On the left side, this is a drawing taken from Scott Aronson's website. Scott's a computer scientist at the University of Texas at Austin, who's a great expositor of quantum information. He's got a very popular blog called Shtetl Optimize that we experts in the field go to. He explains everything so we can understand. And in that picture, this is showing us an important concept in computer science about complexity. So when I say something is hard to solve and easy to verify, this picture captures it. The P at the bottom refers to problems that are easy to solve and easy to verify. The NP on the upper, as we go up and right, NP refers to problems that are hard to solve but easy to verify. Our security on the internet has problems that live in that NP spot. But on the left of it, you see BQP. And those correspond to problems that are easy to solve on a quantum computer, probabilistically. The quantum computer will usually get the right answer, or get the right answer often enough that it's of value and easy to check. Every problem that's in NP that would be used for public key cryptography also lives in BQP. So that picture gives you the concept that somehow a quantum computer is important because our trust in the security of the internet is betrayed by the fact that problems live in BQP. If we could build a quantum computer, we would really have a threat. There's advantages too, but the threat's more interesting to talk about. On the upper right, it's just a diagram explaining somewhat that we're not dealing with zeros or ones. It's complicated, but it's just saying when you're dealing with quantum computers, instead of 0 and 1, you have superpositions. That calligraphic H with the subscript 2 refers to we have to write zeros and ones as some kind of functions. So the math gets a lot harder. And in the lower right, that's an artist's concept of how a quantum computer might work. I think the chip will glow.
So it's, I've gone from thinking about this quantum computer as being this benign and maybe societal changing thing to Frankenstein's monster.
This is the problem in science. That I like to think most scientists are ethical, except some in the movies. And the problem is that, when you discover something, you don't know if it's going to be a threat or an opportunity, or both. But they usually wind up both. So the scientists, you discover a principle of nature. If you read the Frankenstein book, you mentioned that. In the book, the subtitle of Frankenstein is a modern Prometheus, the Greek god who caught fire. The idea of bringing a person to life by parts from a graveyard, bringing somebody to life and getting a soulless, vicious creature. You don't know what you're going to make. So I'm not trying to compare this to Frankenstein, but a great discovery can come with a threat.
And apart from that, I know you've been involved with groups that are working towards the idea of how this would actually be made. How far off do you think a quantum computer is?
Well, there are currently companies that sell computers that are called quantum computers. I'm being very careful here because we have to decide what is a quantum computer. To me, a quantum computer is a computer. It computes the kinds of functions that we know, but there's some quantum stuff inside that makes certain hard problems easier to solve. At the moment, we have demonstrations in principle. So we have computers that have quantum stuff inside and show in small cases it will solve problems better than a regular computer. But a laptop computer is more powerful than anything that you can buy today. So you can buy or use on the cloud a quantum computer and spend millions of dollars, or you can buy a laptop for $1,000 or $2,000 and solve the problem better. So how far off is a quantum computer that will solve problems out of reach of today's is still, I think, decades away.
I see our time is running short. Let's, because I know you've got some other great stuff here. So
I'm almost done. I certainly want to leave some time. So the quantum computer is a threat to cryptography. We have ways to get around it. There are two strategies to save the world from the threat that we're creating. One is to introduce what's known as post-quantum crypto. This is finding new algorithms that we can use that are too hard for a quantum computer. Another one, we don't have those yet, and another one is to do what's called quantum cryptography. And in this picture, there's a slide, and you mentioned in the introduction, I have a part position at the University of Science and Technology of China, which leads the program in China for quantum cryptography. So the slide from the group I associate with shows an interesting thing. And the quantum cryptography makes use of these photons. And the photons, the randomness of whether you see 0 or 1, can be used to create keys. And so there's a satellite that was launched last year, went in operation January this year, and that satellite is able to establish a link at night between two distant locations, 1,200 kilometers apart, that generate keys at a rate of kilobits a second, thousands of bits a second, securely. And there is a plan underway, and it's almost finished, is to also go through the ground. Those yellow lines are optical fibers. And the line builds from Shanghai to Hefei to Jinan to Beijing to have a through ground quantum cryptography link. So China is rapidly progressing to be the first country in the world that will have a communication system that is safe from a quantum computer, if everything goes as expected. There's always surprises. Canada is actually, the Canadian Space Agency announced earlier this year that it's willing to put some money in. So Canada is now slowly progressing towards its own defense against it. And my last slide that summarizes just gives the takeaway message, which people can read. So happy to take questions.
Well, let's get to a handful of questions here. Some of them feel like they get a little deep into the weeds, but let's see where we get. Professor Sanders, could you please comment on EPR paradox and its relationship with quantum communications? This is from John Yang 1.
Okay, yeah. So EPR is Einstein, Podolsky, Rosen dimension. So Einstein had an objection in the 1930s, and the Bell inequality, that Bell violation, is a variant of the EPR. So EPR refers to Einstein, Podolsky, and Rosen. And the question was how we use it for quantum communication. For example, the satellite or on the ground, we can generate pairs of photons, those two green pinpricks of light, green light that I showed, and one goes one way and one goes the other. So let's say one goes to Alice, the other goes to Bob, and Alice measures, she'll see a 0 or 1 if the photon is the polarization of the photon or something about the photon is encoded to be 0 or 1. Bob, the same thing. And if they do it in a careful way I don't have a way to go into, they will then get correlations. They'll have a string where each one has zeros and ones, and they're the same string randomly generated. So that makes use of the EPR paradox.
Very cool. Let's see. We have one from Mohammed who says, what does quantum theory reveal about the nature of consciousness?
Well, so quantum theory doesn't tell us anything about consciousness because the best we can do is write consciousness in the context of quantum theory. And I explained the Wigner-Friend variant of Schrödinger's cat. So, consciousness might tell us something about how to interpret quantum theory. That's a possibility. When I say that quantum theory doesn't tell us a lot, there is work. Roger Penrose at the University of Oxford, Stuart Hameroff, who's an anesthetist at University of Arizona, so in Arizona, and if you look at Penrose's book, Emperor's New Mind, and you look at this kind of writing and various others, they are attempting to use quantum theory to identify where inside the brain quantum theory stops and classical theory begins. So they have arguments about where in neuronal synapses this kind of thing would happen. These are heavily debated topics, but quantum theory, there are people who study quantum theory of the brain, including here in Calgary, also at the University of Alberta nearby, and various other places. And so it could be that exploring quantum theories of the brain could inform studies of consciousness.
We have Phil has sent us a number of questions, and he says, shut up and calculate is fine, but it doesn't help us to understand anything. It explains nothing, which science is supposed to do. I think this is part of a longer chain of
diatribes.
Yeah.
Let me just respond to that quickly.
Okay.
I feel like I'm both a quantum scientist and a quantum engineer. So when I shut up and calculate, my quantum engineering psyche is coming out. So I don't apologize when I'm working on the engineering side of the stuff to just shut up and calculate, but I agree that on the scientific side, we need to continue exploring.
Yeah. All right, Philip, that sounds like a conversation that maybe is more of a philosophical debate, which we appreciate. I'm not trying to push it aside, but there's lots of other questions here. I did mention there was another Schrödinger cat question, which you must get a lot of in your life. Talking about Schrödinger's cat, Elena says, there was a news item a few months ago about scientists detecting Schrödinger's cats in the lab. Could you explain what they were talking about?
Sure. So probably the reference is to a really beautiful experiment that was done at Yale University. And I had a slide where I didn't explain fully, but these I talked about the superconductors and these artificial atoms. And using that kind of technology, they are able to trap light in a cavity. But the light in their case is a microwave. So it's like a microwave oven. And in the microwave oven, you have a field that you use to cook whatever you have in the oven, but they can make two different field states inside the microwave oven coexisting. And so if the two microwave field states are very distinct, we metaphorically talk about those as cats. So they're not working with cats, they're working with superpositions of those field states, and they did one where they can make two cavities, so it's like two different microwave ovens with different cats. So that's the kind of experiment.
Oh, interesting. Not as cute as your waving cats from your slide. Anna Wynn asks, the nuclear wall, is it made of something or is it more akin to a magnetic field? Not something physical, but affect its surroundings somehow.
Yeah, okay, so here's the problem. That, nuclear physics is difficult to understand, and we wind up with different effective theories, liquid drop models and other things. So we have different effective descriptions. And so what I'm referring to is one of the effective descriptions of a nucleus where we replace this, complicated theory of the nucleus by an effective theory that describes certain phenomena and puts a wall around it. So don't take it as a truth that there's a wall around a nucleus. Take it that there is an effective theory that describes some things by thinking of a wall around the nucleus.
This has been really one of the more interesting webinars I think I've ever been a part of, Barry, and I want to thank you very much for taking the time to try to explain this to somebody like me. And I know we had a lot of people online who really enjoyed your talk today. Barry Sanders is a professor here at the University of Calgary and the director for the Institute for Quantum Science and Technology, as well as obviously being a thought leader in quantum science. I want to thank all of you for being part of our webinar today, and please don't forget to fill out that survey. You can also sign up for other UCalgary webinars. We've got ebooks there and videos on the outcomes of all of the scholars' research that we present here in the webinars at ucalgary.ca. Explore collections. Thank you so much, Barry.
Thank you.
The host has left the conference. The conference is about to end.